we can now calculate the response to a periodic input from a linear time invariant system. So using the notation that we've seen before with input x of t, and we've got a system with a continuous time system with transfer function h of s, and calling the output y of t. If x of t is periodic, then we can represent it in a Fourier series. I'll use the exponential form of the Fourier series, sum from minus infinity to infinity of dn e to the jn omega 0 t, where of course omega 0 is 2 pi over t0, the period of the input. We know from the work we've done in previous chapters that the response to the input signal e to the j omega t, if we run that through our system, the output is the frequency response evaluated at that frequency times e to the j omega t. And then since the system is linear, the sum of inputs of this form will produce a sum of outputs of this form. So if the input can be represented in a Fourier series, and we have the transfer function of our system, from that we can get the frequency response, then the output will be dn. Now our input is actually e to the j omega 0 t, e to the j omega 2 omega 0 t, e to the j 3 omega 0 t, and so for each of those corresponding exponential inputs, we'll get in response j n omega 0, those are the corresponding frequencies, times e to the j n omega 0 t. You might recognize that this is in the form of a Fourier series, where of course the Fourier series coefficients of y of t, I'll put a little hat over that to indicate that they're different than the Fourier series coefficients of x of t. These are the Fourier series coefficients of y of t. So we can calculate the Fourier series coefficients of the output from the Fourier series coefficients of the input multiplied by h, j, n, omega 0. Okay. Alternatively, for the compact Fourier series, if we write x of t as c0 plus the sum from n equal 1 to infinity of cn cosine of n omega 0 t plus theta n, then we also know that the output is, we've looked at this in a previous chapter, and we know the response to cosine omega t is, we just scale the amplitude by the magnitude response evaluated at frequency, and then add in the phase angle. So the corresponding output would be c0 times the frequency response evaluated at 0 plus the sum from n equal 1 to infinity of cn, and then magnitude of hj n omega 0 cosine of n omega 0 t plus theta n plus the angle of hj n omega 0. So again, we recognize this as a Fourier series where the cn coefficients of the output are the input coefficients times the frequency response evaluated at the harmonic frequencies, and then there's an additional phase shift that's equal to the phase response evaluated at those particular frequencies. And you can derive a similar result for the trigonometric Fourier series. Let's take a look at an example problem though. So this is problem 6.4-3. I've modified it a little bit where the input is this periodic function. It has a period of 1. And has this exponential decay and then repeats. And it's actually equal to e to the minus t during that first interval. So this is t, and this is this graph of x of t. And we want to determine the Fourier series of the output when we're using x of t as an input voltage, and we're running the input into just a first order RC circuit, R equal to 1 ohm and C equal to 1 farad, and our output is the voltage across the capacitor. And we know with this periodic input from the derivation on the previous board that if x of t has a Fourier series expansion, then y of t will have a Fourier series expansion. In other words, if x of t is periodic, y of t is periodic. The particular Fourier series coefficients for this input are equal to 1 minus e to the minus 1 over 1 plus j in 2 pi. And the period here is 1 second. Corresponding omega 0 would just be 2 pi then. The frequency response of this system is impedance of this capacitor is 1 over SC, so that would just be 1 over S. And so using voltage division, the transfer function would be the impedance of the capacitor over the sum of the two impedances, multiplying numerator and denominator by S. I get this form for the transfer function, the corresponding frequency response. I need to evaluate the frequency response at each of the harmonics. So Jn, our fundamental frequency here, is 2 pi. So I just substitute in for S, Jn 2 pi plus 1. And then so now I have the Fourier series expansion for the output. It's the sum from minus infinity to infinity. I'll call the output Fourier series coefficients dn hat, and then e to the j in 2 pi, omega 0 is 2 pi here, where dn hat are the input dn times the transfer function evaluated at the corresponding harmonic frequencies. So I can write that as e to the minus 1, and then I'll have, you'll see that the denominators here are identical, so I'll have 1 plus j n 2 pi squared. So this is the Fourier series. These are the Fourier series coefficients for the output. In the next video, we'll look at using these expressions and then octave to actually graph what the output voltage looks like with this particular input.